it's a very Earth-centric view.
Yeah.
And what do they always tell you in basic stats? Like, you should never extrapolate from a single data point.
Exactly.
We have the single data point. So, but that's part of what astrobiology gets into is like, does life necessarily have to be Earth-like? Does it need liquid water to survive, or can it exist off ammonia?
Yeah.
Do we need carbon-based life forms, or like the Horta?
Exactly. Hello everyone, welcome to Beaker Banter. We're sitting down with Dr. Michelle Kunimoto, who is an assistant professor in the Department of Physics and Astronomy here at the University of British Columbia. We're talking about planet hunting, the controversy of whether Pluto is a planet, and the real reason why you should visit Las Vegas. So tune in. Thank you to our partner, Innovation UBC, for your wonderful support. So join us as we laugh and learn on Beaker Banter. It's our turn. I'm really excited to talk about planets and space because I never really get the opportunity, other than to my husband, who is obsessed with sci-fi. But on the actual, the actual scientific side of things. So we were having a debate earlier. Can you please define what a planet is for us so we understand this?
Yeah, I mean, even people in my own field have a lot of disagreements over this, to be honest.
Okay.
Because if you were to ask the International Astronomical Union, they have a very specific definition. So for a planet, not an exoplanet, but a planet, it has to orbit around the sun. It has to be sufficiently kind of rounded by its own gravity. So like we used what's called the lumpy potato rule. If it looks more like a lumpy potato, then a sphere is not a planet. But then the third one, which is what drives a lot of the controversy behind Pluto, has cleared its orbital neighborhood. Is gravitationally dominant around other things in its orbit. So Pluto does not qualify because it has so many other objects that are very near it that it isn't gravitationally dominant over. So some people bring up, well, Earth has near-Earth asteroids. You know, it hasn't cleared those out, but it's gravitationally dominant around them. It affects their orbits very significantly. So Pluto doesn't, unfortunately.
No.
So I know, because recently the new NASA chief was saying, I want to push for Pluto.
Exactly.
But it's not NASA that actually makes that decision. We really do kind of fall back on the International Astronomical Union's definition. Now that said, a lot of us don't necessarily agree with that definition, especially because according to that planet definition, an exoplanet, a planet outside the solar system, because it doesn't orbit around the sun, is not a planet. So there have been pushes to get that expanded, and there was kind of an addendum made. But then we've also found these things called planetary mass objects. Or rogue planets, free-floating planets that don't orbit another star. And so are they planets because they don't orbit another star? That's kind of, according to the IAU, they're not planets, but I would consider them planets because they might have been planets at one point.
So that's where I was getting confused, because I knew that your research focused on these exoplanets and free-floating planets as well. And we're using the term planet in it, so not everyone would agree that actually...
Yeah, because some people would just call them planetary mass objects that are free-floating.
But I mean,
why? I like
not just call
rogue
them
planet.
Rogue planet sounds pretty cool.
It does,
right?
It does. A lot of people like to ask me about rogue planets because the name is very cool, and I definitely agree with that.
Exactly. That's what I feel like. Science sometimes is very bad at branding certain things. And they make, we make things way more complex than we need to. As you said, say the full term of what these planets are called by the international.
Well, free-floating planets, if you consider them a planet, but rogue planet, but then planetary mass objects.
Planetary mass object. Why? Why are we doing that? Just call them planets. I don't know.
That would be my belief.
And then you can go into the different types, and that's also something that was really interesting that I hadn't really thought about, the diversity of
planets. Can you speak more to that?
Sure, yeah. So, I mean, we found kind of the first planets just a few decades ago, which is kind of crazy to think about it because it's, well, the first exoplanets, of course. We've known about solar system planets for much longer than that.
Yeah.
But we are constantly surprised by the diversity of planets that we find, and I think in many ways they are stranger than science fiction.
Yeah.
We found kind of the dominant early class of planets were these hot Jupiters. So these are really big, like Jupiter-sized planets that are very hot because they orbit so close to their stars. So they orbit like once every 3 days, whereas Jupiter orbits over hundreds and hundreds of days.
Right.
And so the very fact that we found these hot Jupiters actually caused us to change a lot of the ways we thought about planet formation, because if we look at our solar systems, the big planets are really far away, the close planets are all kind of small and rocky, and suddenly we have these really big gaseous planets that are super close.
Yeah.
And we still don't know exactly how they can exist, but
it's pretty cool.
Yeah.
So what got you interested in space to begin with?
It was a really perfect combination of a few things that happened specifically when I was in grade 9.
Okay.
So I actually didn't know I wanted to be an astronomer early in life. I actually, in one of those like questions they ask you in elementary school, what do you want to be when you grow up? I wrote a librarian.
Really?
But it was, so grade 9 was when my dad introduced my brother and I to Star Trek, the original series.
Nice.
So we started watching that as a group of 3, and I just fell in love with it.
Yeah.
It was also the year that the BC Science 9 curriculum at the time had an astronomy unit. So that was the first time we kind of had a dedicated unit within our science classes about stars and planets and galaxies.
Yeah.
And I loved looking at all the pretty pictures, to be honest. But just like fundamentally changing how we see the universe, I thought was very compelling. And then a third thing that happened the same year was one of my relatives passed away, and he had this small telescope that he would use for birding, just like looking at birds. And it was a small kind of 3-inch field scope, and people were deciding who gets the telescope, right? And because they kind of knew, well, Michelle is being interested in astronomy, sure, why don't they get to have it? And it turns out I brought it to the Vancouver telescope store to get it cleaned, and they said this is the holy grail of telescopes. So this is a Questar, which is a really high quality company that would make these telescopes. And this one was from, I think, like 1967, it's quite old. And it was still in perfect condition. And so I brought that telescope out to my backyard and started looking at Jupiter, and I saw the rings of Saturn.
That's amazing.
And I was even able to pick out like the Orion Nebula. And I think just as a high school student, just seeing that with my own eyes, combined with the whole like science fiction love. And I went to the Star Trek convention in Las Vegas.
Awesome. When you were still in high school?
Yeah.
That's awesome.
The best reason to go to Las Vegas, if you ask me.
Totally.
Yeah.
Thank you so much for tuning in. If you're enjoying the show, please like, subscribe, and share. We also love to see your comments below. Now, back to the show.
That's awesome. So your love for space started young.
Yeah. So grade 9, and then when I was kind of applying for university, I was deciding between engineering, physics and astronomy, and music, actually.
Oh, interesting.
I almost went into
viola.
Nice.
Played a lot of viola in high school, so that was like my backup. But but yeah, space.
That's
so I got into the physics and astronomy program, and
at UBC.
Yeah, at UBC. Yeah. It was actually the only university I applied to because both my parents were there.
Yeah.
It was super close to home.
Yeah.
It's a good university with an astronomy program, so it made sense.
Yeah, definitely. And when you were growing up, leading up to this moment in high school where all these things kind of fell together, were there indications that, science was of interest?
It's hard to say. So both my parents were in, I guess, medical care. Like my dad's a doctor and my mom's a nurse. And I think very early on I knew that biology was not my thing. I found it was just so memorization based.
Yes.
And I know that like biology is a lot more complicated than that, but at least for someone growing up, I didn't necessarily want to go into medicine.
Yeah. I mean, I feel like we don't teach it the way that we should, because if you're in it, it's not.
Right. That's what I've heard when I've talked to people in biology, and I'm like, I have the wrong perception of it. But for whatever reason, it didn't appeal to me when I was younger, and I didn't really think about physics or astronomy until it was kind of that grade 9 moment.
Okay.
So like I said, like I wanted to be a librarian. I was an avid reader.
That's
like
awesome.
I would always be found with my head in a book.
Yeah.
I would just plow through books throughout elementary school.
What
and
were
high
some
school.
favorites growing up?
I loved the Percy Jackson series when I was younger. That kind of evolved along the same time as Harry Potter, which I could read a lot of too.
Yeah.
A lot of fantasy, classic like young adult fiction.
Yeah.
Just a lot of books. So honestly, I didn't think a lot when I was really young about what I wanted to be beyond. I'd figure it out, in high school, and that's what happened. It worked out. Yeah.
That's awesome. So you get into undergrad at UBC, and were you immediately like, yeah, this feels like I'm in the right area?
Yeah, I mean, the early astronomy courses are pretty general, and I do like that they give you this broad understanding of astronomy, and exoplanets was kind of in the back of my mind just because I loved the idea of, seeking new life and new civilizations from Star Trek, studying Class M planets.
Yeah.
But especially there was, in grade 12, there was an event that UBC put on called Women in Physics and Engineering, and it was to encourage a very underrepresented group of students to get involved and interested in science.
Yeah.
So I went with one other student in my graduating class of 350 people to UBC, and we attended a lot of talks from professors talking about the research, and one of them was Jamie Matthews, who would eventually become my PhD supervisor.
Wow.
So Jamie gave a talk at UBC about his work on exoplanets, and he talked about the Space Telescope MOST, which he was the lead mission scientist for, which has done exoplanet work. He talked about the Kepler mission, which was NASA's first exoplanet finding mission. He talked about the transit method, how do we find planets, and he talked about astrobiology. And
what is astrobiology?
Astrobiology it's like the combination of astronomy, biology, chemistry, biophysics. It's a very interdisciplinary field that tries to answer that kind of like, what would life look like on another planet?
Okay.
What makes a planet habitable? What are the ingredients for a living planet?
Right. Okay.
So it brings a lot of very diverse fields together to answer that kind of "are we alone?" question. And actually, that's one of the reasons that I was so drawn to exoplanets, is because it felt like I could make science fiction a reality by studying like actual Class M planets. In Star Trek, those are like the habitable ones.
Okay.
So I saw this talk from Jamie in grade 12, and when I looked up the undergraduate course curriculum at UBC, I found he taught a third-year course called Exoplanets and Astrobiology. And so I kind of had this goal to be able to take it in my upper years, and I think by that point I was pretty sold. Like, I want to do habitable worlds, I want to search for other life, and just like answer that big "are we alone?" question.
Yeah. So let's get into that. Are we alone? What are your thoughts on this?
Yeah, I think statistically speaking, we have to be not alone.
Right.
There has to be other life out there, whether it's intelligent life or microorganisms is a more complicated question. I definitely think that there's microorganisms on other planets.
Yeah.
Intelligent is something that I think there's a lot more that goes into developing that, consistently, and so it might be not. It's hard to say. I love to believe it.
Yeah.
But one of the key things that I focus on in my research is to estimate how common are other Earths. So we have to define what is an Earth-like planet.
Yeah.
It's potentially rocky, it has liquid water, or has the potential for liquid water.
Right.
We have to define sun-like, because Earth-like planets orbit sun-like stars. Not everyone agrees on what a sun-like star is.
Okay.
We have to agree on what even makes a planet potentially habitable.
Yeah.
But as soon as you kind of put some simple definitions on that, we can estimate, given the number of planets we found that meet this criteria, what does it tell us about how common they have to be?
Okay.
And so I did this paper with the Kepler mission with a lot of NASA scientists, and we estimated that about half of all sun-like stars in our Milky Way have rocky, potentially habitable Earth-like planets.
I was not expecting that number.
So if there's hundreds of billions of sun-like stars, you do the math, that's hundreds of billions of potentially habitable planets that have the basic properties that look like the Earth.
Yeah.
And if any one of those, could host life.
That's
I think
amazing.
it's inevitable.
Yeah. It's a huge number. I would agree. I think like just the probability of life has to be out there, whether it's intelligent, that's also another story. And how we define that, right? Because intelligence can be like, even just sensing the environment is a form of taking data in, processing it, interacting with it. But, I want to get into these Earth-like planets because I always wonder, I mean, that's our definition of life, right?
It's a very Earth-centric view, and what do they always tell you in basic stats? Like, you should never extrapolate from a single data point.
Exactly.
We have the single data point. So, but that's part of what astrobiology gets into is like, does life necessarily have to be Earth-like? Does it need liquid water to survive, or can it exist off ammonia? Yeah. Do we need carbon-based life forms? Or like the Horta.
Exactly.
The Horta in the original series of Star Trek was a silicon-based life form. Maybe that's possible. Do we need a rocky planet surface to stand on? Or can, like Carl Sagan hypothesized these gas bag jellyfish-like creatures in the atmosphere of Jupiter.
Cool.
Who knows?
That's sort of where my brain goes. I'm like, why are we restricting ourselves to Earth-like beings?
Yeah, it's really just out of a necessity to simplify the problem, given we have yet to find a second example. So I think that we all recognize that it is a very Earth-centric assumption that life has to look like what it does on Earth, but we got to start somewhere, and so we design our telescopes to try to find those specific types of planets. But I think even within our own solar system, there's efforts to find potential life on Europa, which is a moon around Jupiter. Okay. And it looks completely different from the Earth. Yeah. And it might be the best place to look for life that exists right now.
That's really cool.
So for those who aren't familiar with Europa, it's a moon around Jupiter that is really cold. It's basically covered in this really thick icy surface. Okay. But based off of measurements of its gravity and doing some internal structure modeling, we actually think that there's a liquid ocean right below that icy surface. And that liquid water ocean is in contact with both the rocky core of the moon, which is heated, and the icy surface, which has cracks in it. So you can actually have cycling of chemistry where you have like a heated environment deep in the ocean, kind of like the deep thermal vents we have on Earth, that could kind of drive some chemistry that could originate life. But we also have constant cycling of water in contact with that surface to introduce, organic molecules that might be deposited on the surface of this moon. Right. And so there's going to be a mission launching in the near future called Europa Clipper from NASA that's going to visit Europa and try to confirm that liquid water ocean and just take some more pictures of it. So this is a perfect example of a clearly non-Earth-like environment that nevertheless is very inspiring for the search for life.
So how long would that take, going from Earth to
I don't know off the top of my head, but we'll be waiting for a while.
A long time.
But a lot of progress in astronomy is done over many years, so we're used to it.
And what are some of the techniques that are used to know that that liquid is water? How do we know that?
Well, some of the things that we would do is just look for signatures of the water, like if we think that there's water pooling up from the ocean onto the surface, then we might look for signs of like reformed ice. We've got pictures of the surface of Europa that indicates this is already happening, but if we can get kind of a closer view of it, we might also look for geysers. So like if there's cracks in the ice, there could be water kind of spewing out. We already see examples of geysers on Enceladus, it's a moon around Saturn, which is spewing water. So that's another subsurface ocean candidate.
Okay, so kind of looking for structures, like you mentioned, cracks in the ice and like things that could potentially allow for different reactions to be happening.
Yeah, and there's some concept mission sketches that have been made to actually send instruments to Europa that then bury into the ice and then send little hydrobots to like swim around in the water and actually measure like the composition of it.
Yeah, that's what I'm wondering.
So that would be like far in the future.
Okay.
That's not. I don't think it's been actually funded yet, but it would be a mission concept, right?
Yeah,
so that's the type of thing that we could do. Obviously, an important, almost ethical question around that type of mission would be, we don't want to contaminate Europa with, chemistry from the Earth. So if we're sending something like actually into the water, we would want to make sure we're doing it to the best of our ability to leave Europa as untouched as possible, so that any chemistry or organic molecules that we discover are indeed from Europa, not from
just
the Earth.
us doing
not the us, like not cleaning the telescope properly or
Yeah. So that's years away.
Yeah.
You would say.
Yeah. If it happens at all, but it's the type of thing that we could foresee, in the near future.
And there was just the Artemis mission to get close to the moon so that we can start sending actual astronauts back to the moon.
Yeah.
And can you speak a little bit about the importance of missions like that?
Yeah, I think I always have kind of two answers to like what's the importance of studying astronomy in space and these types of missions. On the practical side, studying astronomy does develop technology that does help us on Earth. Yeah. Like the all the stuff that goes into helping astronauts be able to survive, helps us on Earth. Telescope imaging directly translates to medical imaging that we use. Those are all the practical answers, which I do think are very, very important. Although for me, the personal interest of studying astronomy is always something that speaks very close to my heart, which is just we as a species, I think, are very curious, and we are constantly questioning what life is like, our place in the universe, better understanding our own planet, from a climate change perspective, from a spiritual perspective. And I mean, just the pictures that we've taken from the moon of the Earth, like the Earthrise photo, from the Apollo missions, it just speaks to some core part of humanity, I think. Our desire to understand the world we live in. So I think astronomy is one of those fields that kind of gets at that from a cosmic perspective.
For sure.
Right, in a way that a lot of other fields don't have that really big picture. I think it's like a combination of science, imagination, discovery, curiosity.
Philosophy's in there.
Philosophy, I like to get asked, if we were to find the first sign of life, how would humanity react?
Right.
I think there would be some very interesting philosophical reactions to that type of news. I can't begin to predict what that would look like.
Right.
But yeah.
Well, if we learn from, fiction,
there's
lots of different ways that could play out.
Yeah, Contact is a great example of a science fiction movie that explores that, right? We find a sign of life, and we're having this astronaut reach out to that sign of life, and there's all these reactions from different, parts of the world. So, that's a movie I would recommend.
Okay, nice. We'll put it on the list for sure. So I am wondering, you did your undergrad at UBC and also your PhD at UBC, and then you had some time at MIT as well. So can you talk about why you decided to go to MIT?
So I did my undergraduate honors thesis with Jamie Matthews, the prof I mentioned earlier, on finding planet candidates with the Kepler data set. I basically did the same thing as a PhD student, but just in a better way, because I'd learned a lot over that research position, and I had 4 years to now focus all of my energy on this. And essentially, I kind of wanted to stay in academia, potentially working on a NASA mission or becoming a faculty member eventually. And you kind of, like, at this point in time, you kind of need to do a postdoc to be really competitive to do that. So I applied for a bunch of postdocs. It's an unfortunate reality. It's just become so competitive. So I applied for a bunch of postdocs, and one of them was the TESS mission, the Transiting Exoplanet Survey Satellite, which is NASA's current exoplanet finding mission, at the time was just in its second year of observations. This was in 2020.
So it was pretty new.
It was pretty new, and they were hiring for someone who had experience with looking through, big NASA mission data sets for doing transit analysis to look for exoplanets, and it basically was like tailor-made for my expertise, and I thought, okay, I have to go for this.
This is for me.
So I wrote this application, and the PI of the mission, the principal investigator, George Ricker, emailed me back and he said, hey, we'd like you to come to Boston to give an interview. And we're going to have you give 2 talks, one kind of a general science talk to the Kavli Institute there at MIT and one for just the TESS team. And this was, by the way, this interview was in March 2020. It was,
okay.
At the time, COVID was this is going to blow over in 2 weeks. Anyway, so I flew over to Boston. I gave the talks, and it went really well. I actually had laryngitis when I was there. I don't think I had COVID, but I basically had lost my voice, and I was very stressed that I would not do a good talk because I was feeling very sick. But it went well. So I got the position. They basically offered it to me right then and there, and I said, yes, absolutely. Like, coming to MIT, that's amazing. Because actually at this point I had gotten several rejections from a lot of other postdocs, and I was feeling pretty down on myself.
It's tough, right? It is, as you said, highly competitive.
There's luck involved, absolutely, in the process. So I feel very grateful that the TESS team saw something that they wanted to hire. But 2 weeks, or just a few days after I got back from Boston, they said, if you've been to the US, you have to quarantine, and COVID became a real thing. So that was, I believe I was their first postdoc hired in the pandemic.
Wow.
So I actually spent the first 9 months of my postdoc living in Point Roberts.
Okay.
Because I was told, we're not having any on-campus work, so you technically don't have to be here in Boston, but you do need to be in the US because your position is partially funded through the US government, through NASA. And so I was like, can it be anywhere in the US? And so I lived in Point Roberts, which was a fun experience, crossing the border and explaining to the border people why I have this visa to work in Point Roberts for a NASA mission. Please believe me. I moved to Boston, I think around a year after I started, and I was there at MIT campus, and that was a lot of fun because UBC at the time didn't have a very big exoplanet focus. Whereas at MIT, I mean, there's dozens of people who work on exoplanets.
So what was UBC's focus? Where was most of the research being done?
UBC does have a lot of work in astronomy. I think it's got about 15 faculty members within astronomy. Jamie, my supervisor, mostly worked on asteroseismology, which is like the pulsations of stars. It's about stellar activity. He did exoplanet work, which is why he was my supervisor, but it wasn't necessarily his main focus. There's Brett Gladman, who does planetary dynamics, but he does a lot of solar system work. And then Aaron Boley was a very new professor at the time who has kind of more shifted towards space sustainability, but he also does a lot of dynamics and planet formation. So it was basically those were the 3 faculty members that did something remotely similar to what I was doing. And there was kind of one grad student at the time who was working on planets, and it was me.
Which is, it's good and bad, right? Because then you're becoming the expert on that. So, if you go to your postdoc, you come back, you're the expert in that area. But also, there's no one that can help guide you here.
I think I definitely learned a lot of independence as a PhD student at UBC because the group is so small. But it also really wanted me to, like, when I came back to UBC as a faculty member, I was really excited to build that group. Because I think exoplanets is one of the fastest growing, or maybe even the fastest growing fields within astronomy. And so to situate UBC as a leader in exoplanets was really important to me. And we constantly have graduate students wanting to come to work on exoplanets.
That's awesome.
And so I always have a great selection of people to choose from when I'm hiring my grad students, but that wasn't the kind of the environment at the time. Okay. So when I moved to MIT and suddenly there's highly specialized dynamics experts, formation experts, characterization experts, like so many people to talk to. It was a lot of fun to be kind of part of that really diverse group. Yeah. And so I think as a postdoc, it was a great place to be able to develop my exoplanet expertise, and then bring some of that back with me to UBC.
So can you tell us a little bit about how your research progressed over those postdoc years from what you were doing in your grad studies?
Mm-hmm. So because my graduate studies mostly focused on the Kepler mission data set, naturally it evolved to work on TESS, and I kind of have developed a lot of the code that I've worked on to do planet searches to be mission agnostic. So so there's a lot of missions upcoming in the next few years that I'm really excited by, and I'll be very well positioned to just immediately start trying to find planets for those missions. Okay. With the tools that I've developed. Yeah. So planet discovery remains a very strong component of the work that I do. Okay. And I was able to kind of improve those skills while working actually on TESS. TESS also has a really big goal of doing characterization and follow-up of the planets that it finds. So this is why it explicitly targets really nearby bright stars, which are most amenable to doing follow-up. So that means when we find a planet candidate, there's still some questions about whether it's actually a planet or if it's a star or something else. And we want to do characterization and maybe even characterize like the exoplanet's atmosphere to search for like biosignature gases, things like that. Like that's going back into the habitability question. Right. And so part of my work more evolved in the direction of characterization to do planet confirmation, atmospheric characterization. I got time on the James Webb Space Telescope, which is really competitive. It was super fun. I have a grad student at UBC working on that data right now. Nice. And I think also because I was now in this really rich environment where there's so many people working on exoplanets, my network just grew. Yeah. And networking is such an important thing. Yeah. For grad students, for postdocs. Yeah. Right. So now I have my characterization guy to phone up if I'm writing a paper, or I have this community of other demographics experts who I can chat with, and so what's been valuable is because I was there when I've come back to UBC, my network has become my students' networks, and I think that's been really valuable for them. Yeah, and it's really nice that it's sort of that collaboration across different groups across different countries to come together, because these are big questions that we're trying to figure out, right? Yeah. And it's, as you said, like you can call up this person and say, hey, like I need this expertise. Science is very collaborative. Yeah. Nothing that I do can be done by myself, right? So to be able to have a whole team of people that I'm collaborators with, I'm friends with, that I can call up, even just to like, hey, is what I'm about to propose like really crazy, or
that's the best kind of science. Maybe. Yeah. I always like when I'm writing a grant. It's like your first two aims are like feasible. You've got evidence for them. The last aim, that's the high risk, high reward. Dream big. Yeah. Because I don't want to lose that part of the science. That's the fun part. So I did pull one of your papers. This one is the Searching for Free-Floating Planets with TESS, Results from Sectors 61 to 65. It is open access for anyone who wants to dare to read. So normally when I go through a paper, I like to mark like how many things don't I know here. Okay. This is a lot. This is like quite different from stem cell research, stem cell biology. Like let's see how many. This one was also kind of new for me. It was using a planet detection method that I had never used before. Okay. So it was a little crazy. So there's 17 pages. I'll just tell you up to page 10. There's 18 things I didn't know. And some of those things are like formulas, so there's like 5 things in that formula I don't understand. But if I can get the gist of it. Okay, so we've talked about TESS a lot. So let's just give a bit more background on using that as a tool to actually look at the universe.
Sure, yeah.
So how is it different from some of the other satellites, and how can we use it to look at planets?
Sure. Okay. So TESS is what we call a photometer, which means it measures brightness of stars, essentially. So we can look at a region of the sky and we take pictures of it over time, and then we can use those images to measure the brightness of a star and how it changes with time. And this is a really powerful type of data that we've been using. Kepler used the same data. Kepler was also a photometer. We've been using these for decades to do exactly this type of science.
Okay.
So TESS is, the fact of it, measuring brightness, stellar brightness is not particularly new, but it's just kind of the latest one to do that. So the reason why this is so important to measure stellar brightness is because it can find planets using two different methods. The main one is called the transit method, and this is what I predominantly use for my work. It's what Kepler used, it's what TESS typically uses to find planets. And the idea is, if we're looking at a star and it has a planet around that star, as the planet is orbiting around the star, if it happens to pass basically directly between you and the star itself, it'll block some of the light that the star is emitting, right? And so if you're measuring the brightness of that star over time, you'll see the brightness kind of goes along and then it dips down for a few hours just because something's blocking it. And then it'll come back up. And because these planets orbit, once every 30 days, let's say, you'll see this happen every 30 days. So we can use this method to measure the orbital period of a planet, so how long it takes for that planet to orbit. We can also use this method to measure the size of the planet, so relative to its star. So the bigger the planet, the more light it blocks. So a Jupiter-sized planet will block, 1% of light, and an Earth-sized planet will block 0.0008%, or I don't remember the exact number. It's a tiny number. A very small fraction of the star's brightness. And so Kepler was kind of the first of these class of telescopes that had the precision to see those tiny Earth-sized transits, essentially. And that's why it was so revolutionary. So it observed 150,000 stars simultaneously for 4 years, measuring the brightness of a star every 30 minutes.
That's a lot of data.
Yeah. An analogy I like to give for just how tiny a change of brightness we're looking at is to imagine the Empire State Building at night, which I think has like 6,500 windows. So imagine all of the window shades are up, all the lights are on. Somebody stands next to a window and closes the window shade by a few centimeters. You need to detect the change of brightness from that motion from 100 kilometers away.
Wow.
And remember that these are only going to happen for a few hours at a time before they go back up.
Wow.
And they're only going to happen once a year if you're looking for another Earth, right, in a year-long orbit. And so that's why you need to look at a lot of stars for a lot of time, constantly measuring the brightness. It's a really big deal.
It's such like a small chance that you'll catch it, right?
And to make matters worse, remember how I mentioned how that transit only happens if the planet basically directly blocks the light. But what if it's an inclined orbit, which means it orbits like this instead of like this?
Okay, so
it's not blocking
for those listening and not looking, it's instead of like completely being like aligned and flat.
Like in a plane, like along your line of sight.
It's tilted.
It's like what we say, like face on, for example. Like it basically will not actually, it'll be orbiting the star, but it will never block any light because it doesn't cross in front of the star itself. And so the chance of you having the exact geometry to see a transit is really tiny. Like for an Earth-sized planet in a year-long orbit, the chance is like 0.5%. So you could look at thousands of stars for these transiting planets and maybe just see a few of them, which is why Kepler looked at 150,000 of them, because if we have such a small chance, and we at the time had no idea how common these types of planets were, right? That's why we had to look at so many. So going back to TESS. So TESS basically used the same technique. It uses the transit method. Unlike Kepler, which looked at the same 150,000 stars for years on end, TESS looks at many more stars for 27 days at a time. And then it rotates and then looks at a different set of stars for another 27 days, and it rotates. and over a full year, it covers about half of the sky.
Wow.
So this is really able to give us, it's like an all-sky survey, essentially.
Yeah.
So since the first year, it's revisited at regions of the sky, it's looked at new regions of the sky.
Yeah.
So it's looked at tens to hundreds of millions of stars for transiting exoplanets.
Okay. Wow.
So it's found a lot of planets.
Yeah.
So the transit method is the most successful method used so far, and that's in large part thanks to Kepler and TESS.
Okay.
It's resulted in about 4,700 planets and planet candidates from Kepler, about 7,000 to 8,000 from TESS. And if we look at the total number of confirmed exoplanets on the NASA Exoplanet Archive, which as of today is maybe a bit over 6,000, I think about 4,700 of those are from the transit method.
Wow.
So it's very, very successful.
Yes.
But the paper that you've brought up doesn't use the transit method.
Yeah.
It uses probably the hardest method to explain,
Awesome.
unfortunately, which actually doesn't look for dips of brightness.
Yeah.
It looks at increases of brightness caused by planets.
Okay.
So this is a different effect.
Yeah.
Okay, so what happens, okay, I want you to imagine you're looking at a really distant light bulb. Okay? And there's a magnifying glass that's like moving in between you and the light bulb. And if that magnifying glass passes directly in front of that distant light bulb, you'll see the light from that background light bulb get a little bit distorted and a little bit amplified as that's passing by, and then it'll go back.
Yeah.
So in this analogy, that distant light bulb is a background star, which we call a source star.
Okay.
The magnifying glass is a planet or a star with a planet around it, and the magnification is due to the gravity of these two objects bending the light from that background source. So this actually involves some general relativity, which I will maybe not go into full details, but the basic idea is that gravity bends light and causes these lensing effects, so a magnification of the brightness of these background objects. So even though they are passing in front of that background object, it's the gravity itself that is causing that star to increase in brightness for temporarily.
And that's the signal that you can pick up on.
Yes. So this is a really powerful technique because it can find bound planets around stars. So we'll see an initial, lensing event from the star, and we might see a tinier event from the planet's gravity adding on to that.
Yeah.
But it can also find those free-floating planets we talked about before, because if there's just a free-floating planet or rogue planet passing by, then its gravity will cause this lensing effect.
Okay.
It's a very tiny effect. We call it a microlensing effect.
Okay.
So presumably, if you're observing the brightness of stars over time, like with the TESS mission, if you just search for these very chance-aligned microlensing events, you have the potential to find bound microlensing planets and free-floating planets.
Okay.
And that was the motivation behind this paper, because nobody had ever used TESS to do this.
Okay.
There's some good reasons for it. Why? One of them is TESS was never designed to do microlensing. Microlensing is really difficult to do because these are one-time events. You'll never see, these are completely separate objects that are passing by relatively each other, and so you're never going to see the same microlensing event twice.
Okay.
So follow-up potential is almost impossible. So typically when we've done microlensing, it's been done from the ground using networks of telescopes that look at these stars, these distant stars from different angles, different locations, because if it's the star itself just naturally getting brighter because it's a variable, the timing of that event will be the exact same no matter what direction you're looking at it from. But if it's two objects moving relative to each other, if you look at it from a different angle, in one of them you'll see it a little bit early versus the other one, and so you can show that it's actually two distinct objects moving.
Right.
And TESS never had any simultaneous observations from like a second telescope, so we don't have the same power to do a confirmation of these types of events. So any microlensing candidate that we have, we're never going to be able to really confirm is microlensing.
Okay.
And then kind of another more technical issue is TESS has what we call really big pixels. So if you take like a picture with your camera, right, your image is made up of tons of tiny little pixels, And TESS's pixels are really big. So if you were to take a picture of the sky with TESS, you have multiple stars that will land in the same pixel. And so it's ambiguous which is the actual star in the background that is getting lensed.
Okay.
You don't know for sure if it's like a really far star or a really close one, and that will affect your interpretation of the results. So there's a lot of reasons why it's not optimal.
Okay.
But the benefits of doing this with TESS, which are what motivated the search, is these events are super rare, so you need to look at a lot of stars for these microlensing events, and TESS, as we've established, looks at hundreds of millions of stars.
Yeah.
So it's got to happen at some point.
Yeah, right.
The second is that TESS is a space-based survey, and microlensing is almost predominantly done from the ground. And so the potential for using space-based surveys to do microlensing hasn't really been explored.
Yeah.
And there's a really big flagship mission from NASA called Roman, which is going to be launching hopefully later this year. That's going to be the first space-based microlensing focused survey. So the idea was maybe we could kind of start to explore the sensitivities of these space-based techniques to do this, like in preparation for Roman.
Right.
And we also predicted, given there have only ever been 3 kind of terrestrial or Earth mass rogue planets ever discovered, we really don't know how common they are. And so if we find, a new candidate, then that's really cool.
Yeah, for sure.
These are so rare, and we know so little about their abundance that TESS would be able to help us understand it. So we picked a random sector from TESS. So remember I talked about how we look at this 27 days of data, and then we rotate to look at another one. So each of those regions of sky we look at is a sector.
Okay.
So this is just a random 27-day chunk of data that TESS looked at.
Okay.
And I don't know why I picked this number, but I randomly picked sector 61.
Okay.
Just to,
61
I think
to 65.
it was like, I don't even know if it was like recently observed at the time. I honestly don't know why I picked this number. So basically the TESS mission takes data at a certain cadence, which is basically like how often does it save an image.
Okay.
And the more images over a given amount of time, the better resolution you have over these events, because you'll have more data points per event.
Okay.
So the first 2 years of TESS saved data like Kepler every 30 minutes. The second 2 years of the TESS mission saved it every 10 minutes. And ever since the 5th year, sector 55, it's been saving it every 200 seconds.
Wow.
So I know that I picked like a cadence, a sector that had been observed at this really fast cadence.
Yeah.
And this is significantly more data over a given hour than ground-based telescopes use.
Okay.
So the idea was TESS can give us sensitivity to shorter duration microlensing events and therefore smaller objects. Because the smaller the gravity, the smaller the lensing event.
Okay.
And so we have the potential to find these really tiny terrestrial mass free-floating planets.
Okay.
So we did a search.
Yeah.
Nobody's really done this automated space-based search before, so I just made up my own planet search algorithm that I kind of took from the transit method. I was like, well, instead of decreases of brightness, we're just looking for increases, so I'm just going to flip it and like look at the opposite, right?
Yeah.
And we found something that looked, in our opinion, really promising.
Okay.
Which is a focus in that paper.
Yes.
So there's some plots that you can see. There's this nice symmetric event, which we originally called the microlensing candidate. So we learned later that the microlensing community, unlike the transit community, so for me a candidate means it could be a planet, it could be something else. We don't know. There's ambiguity. The microlensing community tends to define candidate as it is definitely microlensing, but the uncertainty is if it's microlensing due to a bound planet in a wide orbit or a rogue planet. And so when we used the term candidate, they said, you don't know it's microlensing, and they were not very happy with us. So that was interesting, just
Reviewer
knowing
number 2 didn't like it.
just knowing how different communities use the same terminology different ways. So you'll notice that we're careful to not use the word candidate in that paper.
Okay.
I think we use like potential signal or potential microlensing event. But we basically wanted to make sure, given that we only expected to find maybe one out of the entire TESS data set, and we found one in our very first sector.
Yeah.
That was concerning because we thought, how are we so lucky?
Yeah.
Like, either these are way more common than anybody would have expected, in which case that's a huge discovery, or we're doing something wrong. We want to make sure that we're not doing something obviously wrong. So we explored a lot of what we call false positive scenarios. So these are basically scenarios that are just non-planetary. Like it could be the star just randomly getting brighter at that time.
Why would a star do that?
Stars are very variable objects. They naturally get brighter and fainter. Like our sun, for example, goes through these 11-year cycles, which is why we sometimes get like more aurora borealis sometimes than others. It's just higher magnetic activity on the star. So particularly some stars are magnetically active, and that can cause something called a flare, where there's just like this huge quick increase, like burst of energy from the star, and that causes something that might look like a lensing event because it's a quick one-time increase of brightness. So we looked at modeling this event as a flare. We estimated like the energy that would be released from this event if it were a flare, and we found it was orders of magnitude more energetic than the most energetic super flare ever recorded, and so we didn't think it was necessarily a flare. Flares typically have an asymmetric shape, like they're a very quick increase of brightness followed by a gradual decay, whereas ours was very nicely symmetric. So there's a lot of ways you could kind of ask this, and we basically concluded, on the one hand, the fact we found one already is inconsistent with the low expected number of rogue planets we would have found. But on the other hand, we have not yet found a false positive scenario that can explain it nearly as well as the rogue planet scenario. So we don't know what to make of this. So we actually heard, we got a lot of feedback from the microlensing community because everybody has a different opinion on this. A lot of the more traditional microlensers believe it is a flare. They don't think it's microlensing. There's other microlensers who are convinced it is a free-floating planet. And it's not. It can't be a flare. I've shown this to flare experts, and they said this doesn't look like any flare I've ever observed. And importantly, we reached out to a collaborator who ended up being a co-author on this paper, Scott Gowdy, who was very highly involved in the Roman mission that will be launching later. And he said when he saw our paper, this was unpublished. We just posted it for free on kind of this open source archive. And he said when he read that paper, he started to feel really nervous that like flares had never been proposed as a possible false positive source for microlensing. Nobody's ever seen an event that looks basically indistinguishable from a free-floating planet that might not be a free-floating planet, and so Roman needs to think more seriously about how they design their planet search if they're going to be interpreting a lot of these events as microlensing. So basically our results have kind of shaped how Roman is going to be optimizing its search for these rogue planets, and we're planning, I have a student who's going to work with me in September to continue the TESS search. We're going to do all of the rest of the sectors, see if we can find any more of these weird events, and just try to understand how signals can manifest in space-based microlensing surveys for the first time.
It's really cool, and as you said, and I think this exemplifies kind of where we go with science, you're on the verge of something that no one's done before. So you're really like, any result that you have to be really careful about how that's interpreted. And it sounds like you really did go out of your way to reach out to the communities to see what the opinion was, and based on the data, and there isn't a definitive answer as of yet.
And I know we haven't won over everybody. And I still would not say that this is definitely a rogue planet, but I do think it is a signal that is worth better understanding, so that we can do Roman successfully. And I think it's pretty cool to know that this kind of came out of like a conversation I had at a conference with someone who worked on dark matter. He'd never even worked on microlensing, and we were just like, this sounds like kind of a fun project.
Yeah.
And then suddenly we're like actually going to be influencing Roman's development and mission design, and so that was very cool.
Yeah, so it's nice that the impact really has real world effects in, you know, downstream studies, which is really awesome. And then you'll continue to explore what it was, what that might be. Yeah, so I think that's really, I really liked this this paper of what I could understand from my read of it. It sounds really like, I just think the idea of potentially discovering these free-floating planets, what are they, how many are they, and then as you said, as the technology advances, to understand like their composition and what, you know.
Yeah, because again, we have only those 3 discoveries from the ground that are terrestrial mass, and so who knows what their actual abundance is. But one of kind of the main explanations for why they exist is that they probably originated in a planetary system that looked like our own. But then in the early days of planet formation, which was much more chaotic, things were getting, like planets were colliding, they were scattering off of each other, some of them would have been ejected. And some of the early estimates of free-floating planet abundance is that they significantly outnumber the number of bound exoplanets. And so these are potentially the most common demographic of exoplanets, but also the most poorly understood.
Yeah, very cool. So if you were to predict 5-10 years down the road, where do you think we'll be in understanding exoplanets?
Well, Roman is going to be another really big revolutionary advancement here. There have been numbers thrown around like 200,000 new transiting exoplanets from Roman, and thousands of rogue planets and bound microlensing events. And so Roman is going to hopefully be launching September 7th this year, which is my birthday. So that'll be, if it succeeds, it'll be a great birthday present. And so that'll be really cool just to watch over the next few years. I'm hoping to be able to work a bit on Roman data. So I'm already, like my code bases are all ready to start doing planet searches for that. So that's going to find a lot of planets, and especially with the microlensing method, it will find a lot of planets in parameter spaces that we don't have access to with current telescopes. So if you were to look at like a plot of planets by their mass and period, there's regions where we just don't have any detections because they're beyond the limits of current technology, but Roman is going to be able to fill that in.
Awesome.
So very exciting. Next year, there's going to be the Pluto mission, which is a European Space Agency mission that's going to use the transit method to find thousands more planets. So I'm hoping to get involved with that too. 2029 is the Ariel mission, which is another European Space Agency mission that's going to do atmospheric characterization for about 1,000 planets. So that'll be like a population level study of what exoplanet atmospheres look like. That's going to be very cool. So just the next 5 years are super exciting for exoplanets. And then looking beyond that, in the 2040s is when we hope NASA will launch a really big flagship mission called the Habitable Worlds Observatory. So every 10 years, astronomers are asked through this thing called the Decadal Survey, what do you think is the highest priority for astronomy in the US for the next decade? And the answers basically go into NASA choosing what should be their next flagship mission. So the Hubble telescope, the James Webb Space Telescope, Roman, they all came through feedback from the community about what is needed through something like this decadal survey. And in the most recent one from 2020, astronomers said the search for habitable worlds should be the biggest priority for astronomy in the next decade. And so NASA chose this flagship mission called the Habitable Worlds Observatory, which will be the first telescope capable of directly taking pictures of other Earths in year-long orbits around other suns. So it's also going to search for biosignature gases in the atmospheres. So that's going to be a huge advancement for the search for life and the understanding of planets that look like the Earth. So obviously with the, uncertainty over NASA's budget that has been happening, we don't know for sure if this is going to happen, but people are thinking a lot about it. And so if it were to come out, it would ideally be as early as the 2040s. So
that's really exciting. that's the direction that the international community has sort of said, we want to focus now on this.
I think that also speaks to just how much of a footprint exoplanet astronomy has had on the field as a whole. Like I said, it's so fast growing. There's new subfields popping out like every year. It's hard for me to stay up to date on.
I'm sure.
And it's all driven by this like, are we alone question. I think it's the most important question we can ask.
Right. Yeah. And since it is growing, are you seeing more and more students wanting to work with you now? Is that
I think I generally have dozens of grad students, prospective grad students who want to work with me, and I can't pick every single one, but I've definitely noticed an increase in the number of exoplanet interested people wanting to come to UBC, which I think is really cool.
That's awesome.
And a lot of them do want to do habitability related work.
Cool.
So thankfully things like the Plato mission and Roman are going to have applications there too.
Yeah. So now you've been a faculty member for how many years?
A year and a half, almost 2 years now. So I started in July 2024.
Yes. And how are you finding it being, having your own research program and being a professor?
I'd say it's actually gone really well so far. It's a lot of work, obviously, but I felt very supported by my colleagues. So the department has, I think, done a really good job. I have a faculty mentor who I can ask a lot of questions to. One of the things I was nervous about was teaching my first undergraduate class because I've done public speaking for hundreds of people. I've done teaching assistant work as a grad student, for labs, but I've never taught 3 lectures a week to 200 students, first year students. And the department does something called the paired teaching program, where you actually teach the course, your first course, with another prof who's already taught the same course. And so I was able to learn a lot about what goes on behind the scenes of teaching a course at UBC. And that was so incredibly valuable because I wouldn't have known half of it, from the perspective of a student.
Yeah, exactly. Exactly.
So I think that the transition has gone really well.
Nice.
It's still very busy, but I've like I said, I just felt supported, and I think it's gone pretty well.
That's awesome. And in terms of your mentoring style, how would you sort of describe it?
Mentoring style, I think, so I'm currently working with 3 graduate students and 5 undergrads. They're constantly surprising me. I think I really value independence in my students. Like that's a skill that I think that I really want to nurture within my students. Building up really confident and independent scientists. Yeah. Because I think especially like critical thinking skills is really, really important. And if any of them want to eventually become a postdoc or especially a faculty member, you have to think of your own independent research programs. Yes. And I think a lot of graduate students, are happy to have their supervisors tell them exactly what to do. But a really important skill that I kind of had to learn, especially as I was, because there were just not a lot of exoplanet people over my graduate program, was independence. Yes. And I really value that, and it came in really useful when I was a postdoc. So encouraging students to be independent is really important. I also know that especially undergrads, they haven't had a lot of opportunity to work like that. So I typically kind of start out being much more hands-on and then kind of gradually take the training wheels off and let them have more autonomy and command of their research and try to help them get to the point where they can be asking a lot of their own questions and encouraging that. Right. So definitely when I'm kind of choosing which students to hire, I do try to pick people who are very self-motivated and would seem to kind of fit with being a little bit more hands-off, but I've also worked with students who needed to be more hands-on, and then it's just interesting for me to try to teach them how to be more independent.
Yeah, and I think it's really important, as you said, getting those foundational skills, maybe to be a bit more hands-on, you need a bit more guidance in those early years. But if you want to be successful as an independent investigator, there has to be at some point when the training wheels come off, and I think also like we need to be more accepting of it's it's discovery. So so it means that, you know, we are going to potentially make mistakes, fail along the way.
Oh, absolutely, and that's fine. That's part of the process.
yeah, exactly.
Yeah. And I also do recognize that my students all have different, you know, learning needs. They have, some of them really do like me to be very micromanaging, and some of them would be happy if I just leave them alone for a couple weeks, right? Like,
and then it's different depending on the person.
Yeah,
exactly.
so I always like to like work with them, talk about what mentoring style would work best for them. And so far I've had really good experiences with my students. I'm really happy with that.
Yeah.
And like I said earlier, they constantly surprise me. Some of them will even kind of introduce me to a subfield of exoplanets that I haven't focused on, because they'll be like, okay, I know that you don't do this as your main expertise, but I really want to learn about this. And if it's like somewhat close enough for me to be able to study, then I'll be like, okay, I'm going to learn this myself, and so that I can properly kind of mentor you through this. And so it forced me to be more aware of all the rapidly developing fields within exoplanets. So that's been really good. And the students that I've worked with are very inquisitive. They you know, do their own reading about all the papers, not just papers that I send them to read, but like they'll pick out all these other papers and like, oh, have you read this? And I'll be like, no, I haven't. Wow, you're ahead of me.
That's awesome.
So it's been a lot of fun.
So you're learning from them too.
Absolutely. And also just learning how to be a better mentor, because obviously, you know, I make mistakes. I don't explain some things properly, but the more experience that I've gotten over the last 2 years has been really, really good.
Well, I'm so glad that things are going well, and you know, well on your way to growing that research program. So I'm
trying not to think about, you know, the whole 10-year question, which is in a few years. But I think it'll be okay.
I think you'll be. I think you're right on track for that. So I have just a few quick questions as we end the interview here. Just so our audience gets to know you a little bit better.
Okay.
Of the planets in our solar system, which is your favorite?
I think this is probably a common answer, but I'd say Mars.
Okay.
Just because there's quite a few reasons for it.
Okay.
There's the best potential for finding signs of past life on Mars, as we've seen like from the Perseverance rover. So I think that from the perspective of exo-Earth habitability, it's really exciting. There's really compelling evidence for past liquid water running on the surface of Mars. So as a scientifically interesting object, it's really cool. Also, as a science fiction fan, Gustav Holst's planet suite, he made a different suite for all the planets in the solar system.
Okay.
And the one that he wrote for Mars inspired John Williams' Imperial March, the Darth Vader theme for Star Wars.
Very cool.
And so whenever I watch Star Wars, I think about the planet Mars.
That's awesome. I didn't know that. That's awesome.
So it's like it represents that combination of my science fiction love as well as my scientific interest.
Where is your favorite place to see the stars?
I'd say locally, the Gulf Islands are a really good place. So when I was younger, I would visit this place on Pender Island a lot, and sometimes I'd even take out the little field scope, and you can just see so many more stars than in Vancouver, which unfortunately has a lot of light pollution. But I think my favorite place in the world is the first time I ever saw the band of the Milky Way with my own eyes was in Hawaii. So I visited there with my family when I was in high school. And I think I have this vivid memory of just driving down a highway at nighttime and looking up and then be like, oh my gosh, like that's what the sky looks like. And it's why that region is so good for observational astronomy. And it made sense. And it was just absolutely beautiful.
That's awesome. Who's your favorite character on Star Trek?
Spock. When I was younger, my dad used to nickname me Spock. And I don't know exactly why, because I know when I was younger, I was, and I still continue to be very shy. I've had to kind of force myself to be more like public outreachy, but I was very kind of reserved and shy and very kind of scientifically minded, and so he would always refer to me as Spock.
Yeah.
And I thought his storylines in the original series were always compelling, like that conflict of his alien side and his human side, and there's just a lot going on below the surface.
Yeah, great character.
Yeah.
Which of the sci-fi books do you think might be the most accurate?
I'm a really big fan of Arthur C. Clarke as a science fiction writer. You know, for example, he wrote the 2001 Space Odyssey. Childhood's End is one of my favorite science fiction books. So yeah, he's done a lot of really good science fiction that I appreciate the realistic nature of.
Yeah.
And for TV shows, actually, I think The Expanse is a really good example of a science fiction, but like grounded in reality show more than any other show that I've seen. So I'd recommend The Expanse.
I will need to check that out for sure. How many papers do you read a week?
It really depends on what I'm working on.
Yeah.
So if I'm like picking a new project to work on, I will just sit down for hours and just like try to review all the current literature on something.
Yeah.
Week to week, I try to stay up to date on the archive. So archive is like this repository, open access repository where people can just post their papers. Some of them are pre-submission to an article. A lot of them are like after the referee has said, yes, it's ready for publishing. And this is kind of a really good way to stay up to date with the fast field of astronomy. So if a paper catches my eye, I'll read it in more detail.
But it's a good way to just kind of know what's going on out there in the field. What do you think Vancouver does best?
I think just the natural beauty of the city is, I know that's like a common answer because
it's true.
But it's true though. I mean, like I walk to my parents' house every now and then. I live at Westbrook. They live in West Point Grey, and I just walk through Pacific Spirit Park, and I'm like,
it's so beautiful.
This is just in my neighborhood.
Yeah,
it's amazing.
How lucky.
And you know, visiting the North Shore for family there, and just the mountains. It's just so beautiful.
Yeah, it still surprises me like every time I see the mountains. It's just like.
And I'm not actually someone who likes hiking, so I don't take advantage of the natural beauty of Vancouver maybe as much as I could, but nevertheless, just walking around, I take it in.
Nice. I mean, hiking's okay, but like, I'd rather do other things with my time than walk around. Okay, so it's a beautiful sunny Saturday. We know you're not hiking. How are you spending your time?
Well, of course, I just talked about Vancouver's natural beauty, and unfortunately, I would say I'm probably on my computer playing video games.
There we go.
I have, I'm really into a lot of video games. That's kind of one of my main relaxing hobbies, and there's some games that I play with friends online, so I'll probably be found doing that.
Indoors playing video games. Do you schedule free time into your schedule?
I try to.
Yeah.
So this is something I did not do as a postdoc, and it did not work out well. My mental health struggled, I think, and I kind of was forced to reassess the work-life balance, and so it's become really important to me, despite constantly, like, there's that critical voice in my head saying, if you're relaxing, you're not working. But,
I know.
But the more that you overwork, the more frazzled you are, you'll do worse work.
Exactly.
And I know. It was a lesson that was really hard for me to learn, but I'm still learning it.
Yeah.
So I do try to schedule free time. So there's, like, I try to watch a lot of movies because that's like a nice 2-hour, that separates work comes before the movie and relaxing comes after the movie.
There you go.
And I'm not thinking about work when I'm doing this movie. Whereas if I'm like browsing, I don't know, Reddit on my laptop, I'm like, oh, I could tab to my work email. It's like, no. Try not to do that.
Yeah.
So yes, I really advocate, and I tell my students this too, like I really advocate them taking time to themselves, the importance of mental health, and just not overworking yourself to oblivion. It doesn't actually pay off nearly as much as you think it will.
Yeah, important lesson.
Yeah.
It's difficult though, it is.
It's very difficult to learn.
So you mentioned this, right? Like, how are you relaxing and unplugging from work? So a movie, Video games.
Yeah, so a lot of video games. I love listening to a lot of music.
Nice.
Actually, I just took a vacation in the UK and Europe. I followed one of my favorite bands to three different cities.
Which band is it?
They're called TESS. They're from Japan. They're a math rock band. Highly recommend listening to them.
I'll check them out.
And so listening to music, I'm a really big Canadian Football League fan, so I'm like always up to date on how my team's doing.
Nice.
I'm very engaged with the CFL fandom. And so with movies have been really good for forcing me to take breaks because I'll basically like pick a theme of what to do and I'll try to watch every movie that falls under that theme, and that helps me decide what movie to do. Because I find like if I'm just leaving it entirely up to my own devices to pick a movie to watch, I'll just not think of anything and then just not watch a movie. So at least if I have like, okay, I'm gonna watch every single animated movie from DreamWorks and Pixar and Studio Ghibli, like I will just go through every movie.
That's a great strategy.
That's been actually really, really good for me to force myself to take breaks. And I'll watch them even if I know they're going to be a bad movie. So
sometimes that's fun.
So one of the first theme I picked was comic book superhero live action movies. So I watched every Marvel movie, every DC movie. Starting with the 1960s Batman movie. I watched like Howard the Duck, which was technically the first Marvel movie live action. And then I just basically saw how the superhero genre has evolved with time and like how did we get to where we are.
That's so cool.
So I have a definitive ranking of all 130 live action.
Are you going to post this somewhere? Is this going to be?
It's on my Letterboxd page. I don't think it's public.
Who is your favorite scientist and why?
I think mine would be Carl Sagan. Because, I mean, he's a planetary scientist, but I just really appreciate his advocacy for, like, he was one of the biggest early voices about human-caused climate change back in the 80s. Which I think is still something that we're ignoring. And a lot of that has come from our understanding of Venus as a planet and kind of seeing similar processes happen on Earth. But he's also just a wonderful science educator. Like he's given, Cosmos, right? So many amazing videos, and listening to his voice talk about astronomy and the universe it kind of taps into that reason why I'm doing what I'm doing in the first place. And I think he just embodies a lot of that really well.
Yeah, definitely. And where are you going now for inspiration?
I think for like the sciencey answer would be I constantly check in with my colleagues within my own field about like what they're working on. They're constantly inspiring me about where I should take my research and how it would complement theirs. But then more of like a personal inspiration, having just been on that vacation to see one of my favorite bands, like to be just like in a room collectively enjoying something that has brought people from around the world together. I think it's like really inspired me to be grateful for like the community that I have and to just draw inspiration about, I don't know, enjoying what we have, being grateful for it, and collectively like all working towards a shared goal. So that can mean astronomy, it can mean a lot of other things, but I'd say that.
Nice. I think that's the perfect place to end. Thank you so much for being on Beaker Banter.
That's our show. Thank you so much for tuning in to Beaker Banter. Remember to like and subscribe for the latest updates. We can't wait to bring you the next episode. Until next time, dream big, love fiercely, laugh often, and sparkle.